Hello everyone, my name is Vipul Sonil Patil from IIT Gandhinagar. Welcome to CSE 329 Foundation of AI Project Showcase. In this video, I will be presenting an interface Sudoku solver that demonstrates various interface heuristics. This project is built using React HTML, CSS and JavaScript and have hosted on GitHub for easy access. We will be exploring how these heuristics help improving problem solving efficiently, particularly in constraint satisfaction problems like Sudoku. Interface heuristic plays a crucial role in AI by allowing us to make educated guesses and narrow down possibilities, significantly reducing the complexity of finding a solution. In the context of Sudoku, this means we can quickly identify valid number for an empty cell and systematically solve the puzzle. Let's take a quick look at Sudoku Solver and some of its features. This overview will help you get familiarized with the implementation before we get into the code. On the screen, you will see a Sudoku board where you can interact directly. If you hover over an empty cell, possible valid numbers of that spot will pop up. A simple click will let you add or remove a number. You can also have a drop down menu with options like valid domain, backtracking, forward checking, or consistency. These options let you explore how the possible number changes based on the method you select, helping you understand what numbers can fit in each cell. Plus, you can pick any number from the bottom selector to check its probability of being valid across all potential grids. You will also see the probability shifts as we fill more cells. Finally, to really see how the everything works, click on the visualize button. After choosing a method, you will be able to watch step by step how the puzzle solver tackles the Sudoku puzzle, making it easy to understand the mechanism behind each approach. Also, you will have a option to add your board by clicking on set board option and inputting the values you need. As we discussed earlier, we can see valid domain of a blank cell on hover, and on a click we can add or remove a number. We have also seen how we can visualize step by step how each mechanism tackles the Sudoku by pressing the visualize button. Now let's dive deeper into how the method selector impacts the board in real time. I will be first selecting backtracking algorithm. As you can see on the board, when we select the backtracking, the domain for the current hover cell will show the possible numbers. Let's say for this particular cell, the domain shows 1, 2, 5 and 6, and for this cell it is 2 and 6. Now going ahead and adding a 6 here. Notice how the domain instantly updates. Initially, the domain for this cell was 2 and 6, but after placing 6, it just reduced to 2. This is how the hovering mechanism works. As we fill the numbers, it narrows down the possible choices for the other cells depending upon the method selected. You can see the other methods too, like how domain for the blank cell is getting changed for each new input. This behavior is also visible in probability matrix. When we select any number, for example 6, from the bottom numbers and add a 6 here, it affected across the entire board. The probability of 6 being valid in the other cell decreased. This shows how our metrics update the solution in real time, narrowing down the possibilities not just locally but also across the board. And up till this point, we have seen how adding or removing a number affect the board based on the selected method. Now let's take a closer look at how the hover matrix, which shows the possible values for the cell, changes depending upon the method selected. Let's start by selecting the backtracking mechanism. One limitation of backtracking method is that it does not catch the issue that might arise in future. For example, as we are using backtracking here, you can see the hover matrix of this cell shows only one possible number 2, and for this cell it is 1 2 5 8 according to the current state of the puzzle. However, when we switch to the forward checking mechanism, the algorithm takes further constraint in account. In this case, even though 2 appears to be valid in the backtracking approach, the forward checking reveals a potential conflict. When we hover over the same cell, you will see the domain has changed. Originally, the hover matrix showed 1, 2, 5, 8, but with forward checking mechanism, 2 is no longer a part of domain. This is because adding to this cell would cause a domain of this cell to be blank, which is a sign of incorrectness. Forward checking catches this further flow and removes 2 from the possible choices of this cell, leaving only 1, 5 and 8 as valid options. So, by switching from backtracking to forward checking, we can see how the hover matrix for this cell has changed from 1258 to just 158, showing that 2 is no longer a valid option. This demonstration of how forward checking anticipates conflict that backtracking cannot offers a more proactive way and avoid error in solving the puzzle. You can see this update reflected on the board as also in the probability matrix. When if we are originally looking at backtracking algorithm, the probability of number 2 being valid in a specific cell might have been higher, but as soon as we shift to forward checking, you can see the probability matrix updates to reflect the reduced chance of the number 2 get fitting into that cell. This is how forward checking helps in narrowing down the possibilities in real time. Lastly, you can experiment with this algorithm and see changes yourselves by clicking on the link in the description. Whether you are working with backtracking, forward checking, or exploring the probability matrix, this tool will give you a clear visual understanding of how this algorithm works behind the scene to solve the puzzle. Thank you.